We now consider the use of the convolution theorem for the solution of differential equations, for the implementation of systems that are described by differential equations. About the implementation of systems described by differential equations, we have already had some exposure. If you recall, we are only concerned with linear constant coefficient ordinary differential equations, which were given the general form Just to recall the terminology, let us remember that y t is called variously the solution or output, and x t is called the forcing function or input. We had already studied systems described by such equations, and we had even studied certain implementations. If you recall their names, they were called direct form 1 and direct form 2 implementations. All right. Before we proceed, we will make some harmless assumptions, some assumptions that can be made without any loss of generality. This was something we did even earlier, and this is simply that we will assume that m equals n and both are even. If this assumption is not actually valid in a particular example of a differential equation, we can just set n equal to the max of m and n and add a few zeros. For example, if m equals 5, n equals 7, then extend the equation by including A8 equal to 0, that would make n even, and B6 equals B7 equals B8 equal to 0. Then you would have 8 terms of the higher derivatives of both x t on the right side and y t on the left side. So, you could write this equation as summation k equals 0 to 8 a k d k y t by d t to the k, where a 8 is being designated as 0, and similarly on the right side write such a similar expression where b 6, b 7 and b 8 are designated as 0. So, we will proceed with this assumption just because of the convenience it gives us. It, as we can see from what we have shown over here, it does not take anything away from the generality of the formulation. Right. Now, if you recall direct form 1, then it was implemented using a set of integrators and the overall form looked like this. This was the direct form 2 implementation. It required n integrators for an nth order differential equation. Fine. So, this is the only way we could implement, of course, apart from direct form 1, a system that was described by this differential equation. Now, with the strength of the Fourier transform and its convolution theorem, the powerful convolution theorem, there are other ways in which one could implement a differential equation of this sort, a system described by a differential equation of this kind. This is what we are now going to examine. Let us return to the differential equation. Right. Now, suppose we use the differentiation property. The differentiation property says that dyt by dt will transform to j omega y omega, and more generally dk yt by dt to the k, the kth derivative of yt, will transform to j omega to the k y omega. So, using this property both for y as well as for x, we can write down the differential equation by transforming both sides, by taking the Fourier transform of every term of both the sides. This is what we have. Now, let us go on. Recall the convolution theorem. It said that if you had an input x t and an output y t of a linear time invariant system with impulse response h t, then the complete transformation of the following expression x t convolved with h t equal to y t was that x omega times h omega equals y omega. This is the transformation of that equation. But from this it follows that h omega can be written as y omega by x omega. Now, if we go back to the equation we have just obtained by transforming both sides of the differential equation, we find that y omega is a common factor in all the terms on the left side and x omega is a common factor in all the terms on the right side. Hence, we could factorize this expression, divide y omega by x omega to get an expression for h omega. Now, both are nth degree polynomials, the numerator and the denominator. I will call this b of j omega over a of j omega. Then both b j omega and a j omega are nth degree polynomials in j omega with coefficients given by a k's and b k's respectively, b k's and a k's respectively. With these coefficients, right. Now, for a real world system, a system that actually exists in this world and describes some kind of a practical problem, we expect all the a k's and b k's to be real. fine. Now, let us see. This is called the polynomial rational form for the system. Of the transfer function h omega of the system. Now, where is all this leading to? We will know in a very short while. Where it is leading us to is this. You see, earlier as I said, we had only direct form 1 and direct form 2 ways of implementing the system, but now other possibilities open up, and these possibilities open up by manipulating the polynomial rational form in two different but very interesting directions. The first approach is to manipulate a omega by a j omega by b j omega into a product of factors, rational polynomial factors. The second approach is to manipulate h omega into a sum of partial fractions each a rational polynomial. Each in itself a rational polynomial. So, this is the second thing that we can do. So, each of these is going to give us an interesting result. In order to be able to do either of these, the first thing we have to figure out is how to factorize a omega, a j omega and b j omega. So, factorization of a j omega and b j omega. Since all the a k's and b k's are real, this much can be said. We can say that the roots of a j omega and b j omega are all either real or found in complex conjugate pairs. They are all either real or found in complex conjugate pairs. So, what we will try to do is to factorize a j omega to begin with into second order factors, because if we factorize them into first order factors, we may or may not get real coefficients in those factors, but let us just in any case do it to understand what happens. Suppose we factorize into first order factors. Into first order factors. So, we will write a j omega equals pi k equals 1 to n j omega minus I will say p k, where p k are the roots the n roots of a j omega. As long as the pk's are real, there is no problem. If it happens that they are not real, then we will pair them up so that the complex ones are matched against their conjugates. If we match each complex root with its conjugate and develop it into a second order factor by expansion, then finally we can say that we will be able to find an expression for a j omega in the following form. Matching matching conjugate roots into pairs and expanding into second order factors, second degree, we can write a j omega equals pi k equals 1 to n by 2. Remember that we have taken n to be even. Now we know why we taken it to be even, so that we get a nice complete set of second order factors, second degree factors. Then we will write j omega squared plus a k 1 j omega plus a k 0. This will be a j omega will be equal to a product of second order factors of this kind, where we are certain that all a k 1, a k 0, k equal to 0, k equal to (1 to n by 2) are real, because when you match two first order factors with matched conjugate roots and expand it, since the roots are conjugate, all these coefficients a k 1 and a k 0 will come out to be real. In addition to this, there could be some constant outside, which I will call say a 0. That of course will be there, it is just a scale factor that lies outside this entire expression. Similarly, we could do the same exercise with the B polynomial, and following the same arguments make the same claim about the second order factors of the B polynomial. So, we will write similarly B j omega can be written as some B naught, capital B naught, times the product k equal to 1 to n by 2 of j omega whole squared plus bk0 bk1 j omega plus bk0. We could write this. Then, taking this whole thing together, we can now express our h omega as a product of n by 2 different second order rational polynomial factors as follows. Which I will write as B0 by A0 product k equals 1 to n by 2 of h k omega. So, it is a product of each of these factors, and a factor like this is what I call h k omega. Now, let us understand one implication of the convolution theorem. The convolution theorem said that if you applied x omega or x t to a system with an impulse response h t and got output y t, then y omega was x omega times h omega. From this it followed that if you applied y omega further to another system, say h dash with impulse response h dash of t, and therefore a Fourier transform of h dash of omega to get say z of t, then z of t would have a transform z omega which related to x omega and y omega as follows. So, let us consider what is called a cascading arrangement of multiple systems. X t goes to a system with impulse response h t to yield y t, which again goes to a second system h dash of t which yields z t. Let us have this. Then we have y omega equals h omega x omega, z omega equals h dash omega y omega equals h dash omega h omega x omega. Fine. So, this is what we have. Thus, it follows that when you have a cascading arrangement of several systems, then you simply multiply the transfer functions of the respective systems in the cascade, right. So, also following from this, the fact that convolution and multiplication are commutative, it means that you need not even arrange them in any particular order. I could write h dash omega times h omega times x omega equally well as h omega times h dash omega times x omega, or x omega times h dash omega times h omega, in any way I like. The order does not really matter. The order in which we arrange the systems does not really matter as far as the theory is concerned. So, that means if we now look at h omega of our earlier system, let me just put a box on all this. This was a digression. not so much a digression as a clarification of some of the implications of the convolution theorem. We will now return to the original discussion and see the following. Here we are. We have h omega equals some b 0 by a 0, which I will just call say h 0, which is just a multiplicative constant, times the product k equals 1 to n by 2 of h k of omega. Each h k of omega is the typical second order system with both moving average and autoregressive components. How would you implement h k of omega? H k of omega has an impulse response h of t, h k of t, and is equivalent to a system described by a differential equation, right. What is this differential equation that will describe this h k of omega? The differential equation is simple. It has, as you can see, terms j omega squared b k 1 j omega plus b k 0, and on the other side it has j omega squared a k 1 j omega and a k 0. So, this would correspond to the differential equation d squared y t by d t squared plus a k 1 dy by dt plus a k 0 equals d squared x t by dt squared plus b k 1 dxt by dt plus b k 0. If you are not convinced of this, you can again take the Fourier transform of the left side and the right side. Here of course, y t and x t are not the same thing as before. In fact, maybe we should call them as y k, x k and x k, to say that the input x k of t and the output y k of t of the kth system in the cascade. All right. So, you can just take the Fourier transform on both sides and do all the same things that we did a few minutes ago, and you will find that h k omega given by this expression over here, will indeed be given by this differential equation, this difference equation, right. Now, how do we implement this that differential equation in our conventional direct form 2 kind of format? Very simple. You can recall what we used to do. It was simply that if I had x k of t going into the system, then there were a few summing blocks, scaling blocks, and you got y k of t over here, and then you had a pair of integrators, just 2, and then here we had b k 0, here we had b k 1, and here we had the sum of all those. On this side we have minus a k 0 minus a k 1 and then these were getting summed up and added to this. This is how you would implement it. This whole thing is nothing but an implementation of h k of t with x k of t as the input and y k of t as the output. Fine. Now, we have a cascade of such systems. We have a cascade of n by 2 such systems, because the Fourier transform of h omega is a product of all these, plus of course, there is this gain term that was there. Let us just go and recall what the gain term was. It was b 0 by a 0. Okay. So, let us write now a new implementation of a system described by the same differential equation, and this implementation will be called the cascade form implementation. X t goes in to the first block, which is h 1 of t, next block h 2 of t, and so on until you come to h n by 2 of t, and you get y t. In transform domain terms, you would write x omega entering h 1 omega leading to h 2 omega and eventually leading you to h n by 2 omega, and this gives you y omega. So, this is what you would have. This is the cascade form implementation. This is an entirely new way of implementing the differential equation, which you really could not have done, because you had no means to factorize things. The whole thing was in one piece. Now, you are able to factorize them. Now, factorization was not the only approach. If we go back a couple of slides, we will see that there was another approach. That is to manipulate h omega, this one. This one, to manipulate h omega into a sum of partial fractions, each a rational polynomial in its own right. So, this is the next thing we will look at. So, we already have h omega in the form of b j omega by a j omega. Now, depending upon the actual values of m and n, which are the orders of the equation of the derivatives on the right side and the left side respectively of the original differential equation, this polynomial rational form over here for h omega might or might not be a proper fraction, in the sense that the degree of the numerator might or might not be less than the degree of the denominator. If we take the general case that it may not be a proper fraction, then we can always rewrite this as h 0 of omega plus we will write b dash j omega by a j omega, where now b dash the degree of b dash j omega is less than degree of a j omega. This is what this is just done by long division, nothing very special about it. And we have this term, which this h 0 of j omega we will call as the quotient term. It will just be a polynomial. Okay. We have already broken up h omega into a sum of two parts, but this is just the beginning. We are going to break up b dash j omega by a j omega into a series of second order terms, into a sum of second order terms. Now, a j omega is the same as we had earlier, as we had in the cascade form as well, and therefore, its factorization in this case would be really no different from its factorization into second order factors in the case of the cascade form implementation. So, we will again write a j omega as a product pi k equal to 1 to n by 2 product of terms of the form j omega whole square plus a k 1 j omega plus a k 0. This is what we will have for the denominator. So, essentially we are looking at a situation where there are n by 2 second order factors of a j omega, all of which have real coefficients. As far as b dash is concerned, since its degree is less than that of the numerator, after carrying out a partial fractions expansion, what you will get is a sum of sum of terms where each denominator is one of these factors of a j omega and whose numerator is a first order term that is a factor of b j omega, that is dependent upon b dash j omega. In short, you will get h omega, or rather we will just focus on b dash j omega by a j omega can be written as a sum of b dash k 1 j omega plus b dash k 0 divided by, this is for k equals 1 to n by 2. Here you have j omega squared plus a k 1 times j omega plus a k 0. This is what you will have. And therefore, finally, you can write that h omega equals h 0 omega plus this sum. Now, I will rewrite this as h omega equals h 0 omega plus summation k equals 1 to n by 2 hk of omega. Of course, these hk's are not the same as the hk's we got in the cascade form. They are quite different, all right, because these are essentially partial fraction terms, whereas there we had second order rational polynomial factors. So, okay. Now, we have this. How do we implement this? Implementing any hk for k equal to going from 1 to n by 2 is very straightforward, and it would have an implementation like this. It would have an input xk of t that would go into the system b dash k 0, b dash k 1, this would be y k of t, and on this side you would have a dash minus a k 1, and here you would have minus a k 0. That would give you the implementation of the autoregressive part, so that you have this. This would be the implementation of 1 hk of omega. All right. So, this would give me one block. Now, how do I put all the blocks together? In the earlier form, we cascaded all of them, but here we have to add all of them. So, we actually do the following. We apply xt to a kind of a distributor, which passes it successively through h 0 of t, which is the Fourier transform. I am just pointing out that h 0 of t is the inverse transform of h 0 of omega. Then you will have h 1 of t, the inverse transform of h 1 of omega, and so on up to h n by 2 of t. All these would have to contribute to a common sum, and the final result would be y of t. In both the cascade form and the parallel form implementations, we have succeeded in decomposing effectively the larger, more complex nth order system into a combination, either a cascade combination or, as this is called, a parallel combination. This is called a parallel form implementation. We have succeeded in decomposing the larger and more complex system into component systems, either in parallel form or in cascade form, where none of the component systems has a degree or has an order which is greater than 2. This completes our discussion of the study of continuous time signals and their representation through discrete time Fourier series for periodic functions. Sorry, not discrete time Fourier, continuous time Fourier series for periodic continuous functions. continuous time functions and continuous time Fourier transform for non-periodic continuous time functions. We also extended the continuous time Fourier transform to obtain a unified formulation that admitted of both finite energy and finite power signals. So, that we really only need to carry the Fourier transform along with us in our minds. We have seen how the system, this theory of signal representation has allowed us to do many things in a new way. It has given us physical interpretations of notions like frequency, which are certainly easily palpably meaningful in the context of, say, the analysis of music or in the analysis of detail in an image. So, since we cannot go deep into these, into the study of these applications, we will merely point out that one of the truly original things that has arisen out of our study of the Fourier transform as a means of representing systems is signals and systems, is at least these two new, completely new ways of implementing systems described by differential equations. What we have seen is truly a new way of implementing a differential equation, the cascade form as well as the parallel form. These forms of implementation would not have been possible if we did not know how to decompose a higher order differential equation into a combination of lower order differential equations. That could happen only because we used the theory of signal representation provided by the Fourier transform. So, that completes our discussion of the Fourier transform and the Fourier series for continuous time signals. The next thing we will touch upon is the study of discrete time signals and systems which process them, and how we represent discrete time signals, how do we find representations for discrete time signals.